In this video I discuss how a BJT has the ability to amplify, and there's actually two conditions that you need to satisfy in order for the BJT to provide amplification. And before I get into those, I just want to mention again that in the previous video we saw that for these BJTs the base is narrow and also the emitter is heavily doped, meaning it has lots of free charge. So these two fabrication conditions, along with the two circuit conditions that I'm going to show you, all together, these conditions is what gives the BJT the ability to amplify. So first of all, I just want to point out that this circuit that I'm showing with the physical aspect of the BJT, along with these two sources, this is the most common type of configuration called a common emitter, since the emitter is connected to both voltage sources. But this is not a practical circuit because we don't have any resistance in these paths here. So you wouldn't want to actually take a BJT and connect sources directly up to the base emitter and collector emitter like I have here, because you would burn up the transistor. But this discussion is just for conceptual reasons, and I wanted to keep the circuit as basic as possible. In a future video we'll actually look at a practical BJT amplifier circuit that does have resistors in these paths. First of all, one condition that you need in order for the BJT to amplify is you want the base to emitter junction. Okay, remember we have a PN junction between the base and the emitter and a PN junction between the collector and base. Well, you want that base to emitter junction to be forward bias. So if we assume we have a silicon transistor here, that means you want VBE, the voltage across the base to emitter, to be equal to the turn-on voltage, say 0.6 volts. And what results is that you'll have a current that flows in this loop right here that we call the base current. Okay, meaning that these free charges that are in the heavily doped region are contributing to this base current. So now we have charges that are passing through this middle region here, the base, through the emitter in a path like this. Now, in addition to having base current flowing due to this base emitter being forward biased, the other condition that we need in order to get the transistor to amplify is that we need the other source value, VCE, to be at least 3 to 4 times VBE. Okay, so you need this source voltage to be at least 3 to 4 times bigger than VBE. So it's got to be at least 2 volts or greater. Okay, if we have a VBE, say of 0.6, then roughly VCE would have to be at a minimum 2 volts or something greater than that. And the reason you need VCE to be this value here is because now when the free charge gets up into the base region, it's going to feel a greater attractive force to the collector. Okay, so what results is that you have a current flowing in this path, okay, that we call the collector current. And because VCE is at least 3 to 4 times greater than VBE, you're going to get a much larger current in this path here. So you see these two circuit conditions, along with these two fabrication aspects of the transistor, is what gives the BJT the ability to amplify. Because now if I connect this transistor up into a circuit with resistors and say some signal that I want to amplify, like some sort of AC signal, well, if I make the base the input to that circuit and I make the collector the output of that circuit, well, having a much larger current at the collector, the output of the circuit, compared to the base, the input of the circuit, well, I can get a bigger voltage signal at the output of this circuit compared to the voltage at the input of this circuit. And that's how we get amplification, or an amplified voltage signal with a BJT is through its ability to essentially amplify the current, right? Through Ohm's law, it should make sense that if I have something that can amplify current and I put it into a circuit that has resistances, well, voltage is just I times R, and I could have the ability to get a larger voltage with that transistor in the circuit. And we're going to cover examples where you see exactly the analysis where that is the end result. Now, just a few equations here before we talk about the IV characteristics of a BJT. One is that current gain which is represented with the symbol beta, is just equal to the ratio of collector current to base current. And typically the current gain of a BJT being used as an amplifier is in the couple hundred to several hundred range. That's not uncommon. Now, there is a spec item, an item that you'll find on the data sheet of a BJT. Okay, so there's something called beta spec. This is beta. Okay, so again, you would find this on a data sheet. Okay, BJTs have data sheets just like diodes and any sort of component. And this beta spec, this is the optimum beta. Okay, this is the max beta that the transistor has the ability to provide based on its fabrication. Okay, and we'll talk more about beta spec coming up here. Okay. One other equation is that, as you can see here, the current at the emitter is just the addition of base current and collector current. At this point, these two currents combine. So emitter current is just the sum of base current and collector current. And often emitter current is just approximated to be equal to the collector current, since a lot of the times the collector current is going to be at least a couple hundred times greater than what the base current is. Alright, the next thing to look at is the IV characteristics of a BJT. Just like you saw in your circuit theory and just like you saw in this class with diodes, all components in a circuit are defined by their current voltage relationship. A BJT actually has two IV relationships that define it, one at the base side and one at the collector side. Here's its IV characteristic at the base. You can see this is base current versus base to emitter voltage, and this curve should look familiar to you, okay, because you can see here it's sort of like an exponential type of curve, where at 0.6, 0.7, that's when we start to get an appreciable current. And if you look back in previous videos, or you look back in your notes or in the textbook, you should be able to recall that this is the IV characteristic of a forward bias actual diode. And that shouldn't come as any surprise, because as we mentioned earlier, between the base and the emitter, where we have our base current flowing, right, and VB is across that base to emitter part of the circuit, well, that is a PN junction, that is a diode. And one of the conditions for amplification is that that junction needs to be forward biased, and it has the drop of 0.6, so it's a turned on diode. And that's exactly what this IV curve shows. Alright, now that's not the only IV characteristic that defines a BJT, because we also have to look over at the collector side, and this is what collector current versus collector to emitter voltage looks like. And what these various curves are here these are constant base current curves. So all along this curve here, you have a base current of 2 milliamps. Okay, so here where it's relatively flat, and then here where it dips down, all along that curve is 2 milliamps. Likewise, all along this curve is 4 milliamps. Okay, 6 milliamps. See, there's really an infinite amount of base current curves, and only a handful or so are being shown in this diagram. And what determines which base current curve you're on is the values that you have in this part of your circuit here, VBE, along with, in a practical circuit, as I mentioned earlier in this video, we'd have resistances here. So based on what the voltage and what the total resistance in this path is, that's going to determine what your base current is. Now, the most important aspect of this curve to note is that right along here, roughly right about 2 volts or so, that's where these curves start to bend when you have a VCE less than, a couple of volts. And then to the right of where VCE equals a couple of volts, that's where these curves are relatively flat. Well, in the region here, okay, in this region where the curves, okay, the constant base current curves are relatively flat, that means your beta, which remember, beta is just collector current divided by base current, well, that's where your beta is relatively constant. And not only is it relatively constant, but in this region where the curves are flat, the beta, for all practical purposes, is the optimum beta. It's the largest beta that transistor possibly can provide based on its fabrication. So when you look on a spec sheet and you see what the beta spec is, that's roughly what it's going to be in this region where the curves are relatively flat. So you can see with this transistor right here, the beta spec is roughly about 100, because if you take this curve right here, the 2 milliamp base current curve, well, come on over to the collector axis and you have about 200 milliamps. So your beta is IC versus IB, so, or excuse me, IC divided by IB. So 200 divided by 2, that's 100. And again, since we're in this flat region, that's roughly what your beta spec is. And this is where you want to operate the transistor when you operate it as an amplifier. You want to be in this region here where the curves are relatively flat. We'll see later that when you operate the transistor as a switch, you either want to be close to the VCE axis, because that's when the transistor is going to act like a switch that's off, or you want to be real close to the vertical axis, because that's where the transistor is going to act like a switch that's on. Okay, but that's for later discussion. Now, it should make sense to you based on what we talked about earlier, why this bend in these curves happen at about 2 volts. Because if you go back to one of our conditions for amplification, okay, the second one, that you want VCE to be at least 3 to 4 times VBE. Well, that's to get this collector current to be much greater than this base current. See, once VCE is not at least 3 to 4 times VBE, once this voltage source value here between the collector and emitter approaches what the base to emitter voltage is, well, you get a more evenly split of the free charges through the transistor, which means that the ratio of IC and IB are going to approach 1. Okay, and you see that's what you're seeing here in this plot when VCE is less than 2 volts. See here where the curves dip, your beta is decreasing, right? For example, here again on the 2 milliamp constant base current curve, once I hit this downward slope here, there's still 2 milliamps of base current, but now I'm going to have less collector current, so my beta, my current gain, IC over IB, is going to be decreasing along this slope, okay, for any of these curves. So you see, that's why you don't want to be in this region here when you use the BJT as an amplifier, because you're not going to get the optimum gain that you get in the region where the curves are flat. Okay, last item here is just some terminology. Okay, here's the same IC versus VCE plot. This region where the curves are relatively flat, where you would operate the transistor as an amplifier, is called the active region, so know that term. And then the two other regions where you would operate the BJT if you were going to use it as a switch. Well, here where the BJT acts as an off switch is called the cutoff region, which was cut off from our view. And then this region here along the vertical axis, this represents when the BJT is acting like a switch that's on, is called the saturation region. And we're going to talk more about both looking at practical circuits of a BJT amplifier and also practical circuits of a BJT switch.